Hey everybody, this is Miss Darty. So today what I want to go over is your molecule shapes activity and introduce a concept called VSEPR. VSEPR, or VSEPR, is a theory, and VSEPR is an initialism that stands for valence shell electron pair repulsion. And what that means is that the valence electron pairs are going to try to get as far away from each other as possible. They are like charges, so they are going to repel each other. And so when you put valence electron pairs around each other, they are going to get as far away from each other as possible, and that is going to affect your molecular geometry. So we have a molecule here that has two bonded atoms. And if we show the bond angles, you would see that the bond angle is 180 degrees. And if we were to show the molecular geometry would be linear. Now, if we add a lone pair of electrons, that's going to drastically change the shape of the molecule to where we have a 120 degree angle and the molecular geometry is bent. If we add two lone pairs of electrons, that doesn't change the shape of the molecule, it's still bent. This is one of the only times that adding a lone pair would not affect what we call the shape of the molecule. But if you notice, the bond angle has drastically changed. It went from 120 to 109.5. And so we have decreased the bond angle because we have added a lone pair, which is going to repel the other valence electrons in this molecule. So let's go back to our regular molecule and let's add a linear molecule. Let's add a bond, another bond. So here we have another bonded atom, which changes the bond angle to 120 degrees, and notice the molecular geometry is trigonal planar. If we add a lone pair of electrons, the bond angle is going to change to 109.5, and the molecular geometry has changed. This looks severely different than just the three bonded atoms, the trigonal planar. This molecular geometry is called trigonal pyramidal. If we take away a lone pair and add another bond, we get the bond angles to change to 109.5, and this molecular geometry is called tetrahedral. If we add another bond, we are going to get the bond angles to change to 90 and a molecular geometry change to trigonal bipyramidal. And one last bond is, so we have 6 bonds now, bonded atoms, I mean, and the bond angle changes to 90 degrees, and that would be octahedral. So adding bonded atoms, adding lone pairs of electrons severely change the molecular geometry. Lone pairs are going to repel each other more. So that is the lone pairs decrease the bond angle more. And so it doesn't show it in this demonstration, but it is, the lone pairs do repel each other, the other bonded atoms more. So another point that I want to make is that when we put double bonds, it does not change the bond angle or the molecular geometry. So we can have one single bond and one double bond, and this molecule still be linear. We could have two double bonds, and this bond angle still be 180 degrees, and this molecular geometry still be linear. We could have two single bonds and a double bond, like NO3 -1, which is still, the bond angle is 120, and the molecular geometry is still trigonal planar. And then you did the real molecules examples, so this goes into some real life examples. This is water, and you can see that the molecular geometry of water is bent. And so you went through this and did all of these. This is carbon dioxide. The carbon dioxide is a very simple molecule. It is linear. And so this is the VSEPR, the molecular geometry activity that you did, the molecular shape activity that you did. And so I just wanted to go through that and reinforce some ideas. Thank you very much for learning with me today. I enjoyed learning with you.